In this video, we're going to look at divergent sequences. We start with the definition, and the definition of a divergent sequence is given right here. And basically what it says is that the sequence doesn't converge to anything. In other words, to understand what a divergent sequence is, we need to negate this particular definition. So I want to start with that process of trying to negate the definition of a convergent sequence very carefully in order to understand what a divergent sequence means. So let's get started. I want to start by writing down the definition of convergence in a symbolic, kind of a half English, half symbolic way of using notation. So we want to remember that a sequence converges to a particular x. That means that for every open interval S containing x, there exists a natural number capital N, such that the entail of my sequence is a subset of the open interval. So what this means is that the sequence does not converge to a particular x if and only if we have the negation of this whole mess. And I want to take the time to negate that very carefully. So I want the negation of, for all open S's containing x, there exists an n inside the natural numbers such that the entail is a subset of the open interval. Now, to negate this particular compound statement, it is a doubly quantified statement, I'm going to negate it in parts. This statement is equivalent to there exists an S that contains x such that the negation of there exists an n inside the natural numbers such that the entail is a subset of S is true. So now what I'm going to do is negate the second quantifier. So we have there exists an open interval S that contains x such that the negation of an existentially quantified statement is a for all. So for all capital N's inside the set of natural numbers, we have the negation of the entail is a subset of the open interval. And we can finally clean this up and get there exists an open interval S that contains x such that for all n inside the natural numbers, the entail is not a subset of S. So this last statement is what we really mean when we say that a sequence does not converge to S. Now we actually have to figure out what this means. So let's look at the next page and try and get a handle on what this means geometrically in terms of the topology of the real line. So we have the sequence does not converge to x means there exists an open interval S that contains our point x such that for every capital N inside of the natural numbers, The tail, the entail, is not a subset of my open interval. Now, I want to think about what this actually means. So what does this part here mean? So let's draw a picture. So here's my number line. Here is x, and I am assuming that the pKs do not converge to that x. So I want to take some, what I have is there is some open interval. So what we're going to do is we're going to say, we have found an S that loosely works. And by works, I mean it satisfies this. So here's my open interval S. Now I know that no entail is a subset of this particular S. Now what does that really mean? Well, that means that if I pick an n inside the natural numbers, then there is always going to be a little m bigger than that capital N, such that Pm is not inside my set S. So Pm has to be out here. But I'm going to call this, this is going to be my first one. Now the thing is if I look at capital N2 that's bigger than little m, I still have to have an M2. Let's call that one M1. That is outside of set S. So there's going to be a PM2 that is also outside of S. And I can keep doing this. It turns out that we have to have an infinite number of terms of the sequence that lie outside of this open interval S. And I want to make it very clear why this happens. If we had only a finite number of terms that were outside of this open interval S, then we could find an entail that is a subset of S. And here's how we would do it. Here's my number line. Here's X. Here's my open interval. We're going to assume that the only terms outside of S are, I don't know, PM1, PM2, PM3, all the way down to PM, and I'm just going to call him last. This is the last P that is not inside S. In other words, I can assume that M1 is less than M2 is less than M3, all the way up to is less than M last. So PM last has the biggest of all of the subscripts that are not inside S. So PM1 is out here, PM2 is out here, PM3 is out here, and all the way down to somewhere PM last is out here. But what does that say? That says if little n is bigger than m last plus 1, then Pn has to be inside S. So Pm last plus 1, and the rest of the tail is in here. So Pn is in here if n is bigger than m last plus 1. In other words, this says that S does contain a tail for my series, for my sequence. And that is a contradiction to the fact that we had assumed that S contains no tail. Now, the upshot of this is the following. To show that a sequence does not converge to X, we must find an open interval containing X and an infinite number of terms of the series are not in the open interval S. And that's all that we have to do to prove that a sequence does not converge to S.